undergone to a flow like this, and this is the flow, and we're supposed to have a supersonic flow, and we have written here the equation regulating the unknown vertical displacement. The unknown vertical displacement of this structure is the displacement W as a function of x and t. X is this axis here from 0 to L, and time, and W is the vertical displacement of this panel. We are studying this panel as a simply supported beam, but we could generalize this into a plate structural element instead of a beam. However, for sake of simplicity, we consider here a beam, and therefore we have an elastic force imbalance of the beam here. We have this contribution, which is a bad spring contribution like this, and then we have this contribution here, which is the buckling term as arising by this load. This load is a static load, and therefore we have this m bar here as compressive force, and we have this parameter here influencing the second derivative of the displacement. Next, we have the inertial forces in the balance, and at the beginning we consider this pressure distribution P as a function of x and T as a function, as a generic function of the location x and time. But, and this is the point of elasticity, we suppose to calculate this pressure as a function of the displacement of the plate. And we assume as a theory for doing that the accurate theory, and therefore this pressure is equal to a constant, negative constant here, multiplied by the first derivative of the displacement. In other words, this first derivative is indicating the angle theta between this theta. If you consider this plate and you consider a deformed configuration like this, in this point here, theta is the angle between the tangent to the plate and the reference horizontal axis. Okay, this theta is, for the case of Euler-Bernoulli theory, is equal to the first derivative of the displacement itself. So this term is initially on the right hand side as a forcing term, but whenever you are able to express this term like a proportional quantity by the state space variable W, you are able to move this term on the left hand side here as part of the system, as we discussed it yesterday. We have to discuss also these last two terms here, the yellow one and this here, and these two terms are a term indicating a first time derivative of W, indicated by dot. Dot quantity are derivative with respect to the time is dot with the dot here, and the prime is the derivative with respect to the x. So the derivative with respect to x, okay, use another symbol, star. Star. The derivative with respect to x of star is star prime. So use prime and use dot for indicating space and time partial derivative. So these two terms multiplying the first time derivative are damping term. In particular, this here is a structural damping as proportional, and C is the constant of proportionality of the stiffness here. So we have a fourth order space derivative plus one order time derivative here. and it's so indicating the time derivative of a term proportional to the elasticity with this coefficient of proportionality. And this here is another damping term, but associated to the aerodynamic. And so we have this mu multiplying W dot. If you study in gas dynamics the simplified Agar theory and eventual extension, you have for the pressure this quantity. So here we could add here also the yellow term related to the damping aerodynamic. Just here, I can see the where is okay. So plus mu or minus, excuse me, minus we have minus, what is it? Okay, minus mu W dot. Okay? Okay, at the end of the story, we have a partial differential equation with initial condition together with boundary condition. Initial condition, boundary condition, excuse me, and initial condition in time. The boundary conditions are the standard boundary condition of a simple support beam. So zero displacement and zero moment at the hinge. So zero, the moment is related to the second derivative, and therefore zero second derivative at the edge of the beam. And for the initial condition, we are currently assigning a shape, an initial shape, and an initial field for the velocity for the panel. And then now go and find the solution. What we are talking about? In the physical point of view, we are talking about this problem. Can you see? Oh, yes. Can you see the screen here? Can you?
Yes.
Okay.
Yes.
Here we are inside a wind tunnel. This is a wind tunnel. This is the door of the wind tunnel for the incoming for the outlet of for the air. And this here is not a window. This here is a panel. Is a flexible panel, and this here are Scotch tape strips applied on this metallic panel. So we have a wind incoming in this. And what happens when I turn on the wind tunnel? What happens is exactly what one expects, is the following. Okay? And this is what we want to study. The wind is the flow is flowing upper the panel, and we have a pressure distribution applied on the plate. The plate deform, but the formation of the plate are able to influence the flow distribution, the pressure distribution. So we have a coupled mechanism, and the result is the following. Okay, it's very common experience. So we want to study this exactly, and for this scope, the study of the system is very interesting because in the mathematical point of view, we have to study a partial differential equation. And the first step for solving this problem here, the first step is transform this PDE problem, this partial differential equation problem, in a ordinary differential equation problem, only in time. And this is a mathematical approach, also known as eigenfunction method. And most of you are confident and know this approach in previous course. Other people may not. I will give just a brief, very brief representation of this technique. The technique is the following. Essentially, we have an equation to be solved. Ok? But, excuse me, sono a lezione, Annalisa? Niente, ciao ciao. So we have a question, an equation to be solved like this, and we try to represent in space this equation. This equation is a function of x, a function of time. Instead of solve this, imagine to represent this by series of x function like phi n of x. We have many of these functions like this. Imagine, assume, and so we would like to express this quantity as a summation of quantity like this and like this function time. Now, the point is the following. This could appear like an approximation. Please, thank you, the United States, for visiting of this secretary just here in the Colosseum. We are full of noise, full of helicopter noise because of the presence of State Secretary of the United States. Thank you. Okay. This position could appear like an approximation because nobody will be able to guarantee to you if you can do this. But look the parallel with the vector. If you have a vector, can you represent this vector as the multiplication of a base component by a component v plus another base component by a component v plus third component by component v3? Can you do this? The answer is yes, you can, but you are sure that the basis vector are independent. Okay? Yes. If independent, E and the space spanned by E1, E2, E3 is the full space. So you have to be sure that you are able to cover all the space. Yes, if independent, and all space is covered. No, it's spanned, better. Now, this is what happens for the vector. And what about the function? Because we have not a vector here, we have a function of x. Okay? For the function, we have the same, because a function of x like this, like f, supposing to frozen the time, and for time frozen, you have a function of x. This function of x is the contribution of the several value assumed by the function from x equal to 1 to x equal to L. So you don't add three components for build this vector, you have infinite components to describe this function. Okay, so you are practically in front of a vector of infinite dimension, a function. Okay, and parallelly, here you can represent this vector as the sum of three base vectors combined by the component En vector by Vn, and this is exactly the same we did here for the function. You are assuming to represent f, x in any time frozen or prescribed, like the summation of this function of x by w1 t frozen plus function 1, function 2 of w2 t plus infinite. Why infinite? Because the space is infinite dimensional. Okay? This is an important note. I am building together with you this concept, avoiding approximation. This is an exact position. It is not an approximation. I don't talking about separation variable is approximation. No. It's exact. If you have independent function, it is correct. Okay? An example of two independent function. I don't know if you have a function phi1 x like this, in this domain, like this, and another function phi2 like this. Are these two functions independent? Yes, because you can't express this as proportional to this other one. Okay? Okay. Now, first step. Second step. The second step is about the component. What about the component of this? I'm not able, in general, in the vector theory, to calculate the component in general, but you can do this in the case the base is orthogonal. So, look, if sto facendo lezione, Fulvio, scusa, ti richiamo. Niente, ciao. Well, if you have an orthogonal function, if you have orthogonal vector, again, if ei dot ej is equal to delta ej, which means equal to 1 if I equal to j and equal to 0 if I is not j. If you have an orthogonal function, you can evaluate, for example, v2. How can obtain v2? You have v equal to e1, v1, e2, v2, plus e3, v3. Okay? You can multiply both sides of this equation by e2 because we want to calculate v2. I know that this is trivial. I know. But this is the exact parallel between the theory of vector in finite dimension and vector in infinite dimension, which is the theory of functional analysis. Okay? So if you multiply by E2, you have E2 dot V is equal to E2 by E1 is 0. E2 by E2 is 1. E2 by E3 is 1, is 0, excuse me. And therefore you have V2, okay? And eventually, if your basis is not orthogonal, you have here E2 dot E2. And so, as a final result, V2 is equal to V projected to E2 divided by E2 dot E2. Okay, so if you have an orthogonal basis, the component can be found as projection. Now, look what happens here. If you have independent function, excuse me, let me write. I have do a little bit mistake. This f is our differential equation, and the component, the proper noun for the component is f1, f2, and so on. So we have two different representation in terms of series: the equation and the unknown. So please correct here. Let me do this. This is not 0. This is equal to W, X. So please, this is the equation, and this is our unknown. So I am applying the vector representation for both of them, the equation and the unknown. Okay, for each time. The equation is known, the unknown is not known. Excuse me, this, okay. So in the case of the equation, I have that this is 0. But look here. This f, capital F, is now represented on the basis of psi 2. And what I prescribed in the equation is that capital F is 0. Instead of saying capital F is 0, we say this series has to be zeros. Of course. But if the base functions are independent, these are independent, the fact that capital F is 0 implies that all the F components are 0. This is an important point, guys. Okay, again, let me repeat this point. If you have a vector here on the left-hand side, and this vector is 0, if v is equal to 0, necessarily v1 is 0, v2 is 0, and v3 is 0. Okay? Why? Because your bases E1, E2, E3 are independent, and this is a necessary condition. It's the same for the function. If you have a function f expanded with a series of independent, as a combination of independent functions, this function is 0, necessarily the component has to be 0. And the component now are f1, f2, and f3, and so on. Okay? Probably in the first time of your life, we are robustly discovering the famous Gagliarkin method. Now, this is necessary, but do not forget that you have to solve instead of one equation, now you have to solve infinite equation. Because this series is infinite, because the space has an infinite dimension, the space of the function has an infinite dimension. And therefore, if you write here equal to 0, you have to put equal to 0 all the infinite function f1, f2, f3. And what about f1, f2, f3? I don't know. f1, f2, f3. No, 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 no. You know very well. In the case these 5 functions are orthogonal, if adesso, here is independent only, but if you have the information of orthogonality, then 0 component means 0 projection. And projection is project. This is the symbol of projection. I will define this later, don't worry. Project f as a function of x and t. Project your function on each function phi. And this is f capital Fn. In fact, this demonstration is quite similar. You have f equal to phi1 by f1 t bar plus phi2 by f2 t bar plus phi3 and stop it plus all the other. Now, as before, take the inner product, the scalar product of this in both sides by phi2, for example. So do this. Dot product, scalar product by phi2. This symbol, in this case, is an integral. The integral of the function circle by the function star in the x from 0 to L. This is our space domain, the domain from 0, x domain from 0 to L. Okay, so this is the definition of my inner product. Consider that the inner product is the following. If this is the circle function, and this is the star function, how can you do the inner product between these two functions? In the case of this vector, finite dimension, you take A1 component by B1 component plus A2 component by B2 component plus correct? And here you have to multiply this value of star function by the corresponding value of circle, and then sum, the integral. And this is exactly what you do here. This is the inner product. This is the dot product for the function. Okay? So, go back to our problem. Here, we have this function, and we are taking the dot product, the inner product, for all this quantity, all this quantity by common phi2. Okay? Of course, I have an identical definition for orthogonal function. Two functions are orthogonal if and only if, when you take the inner product between one function and the other, you have 0 if m is equal to n, and you have the scalar product phi n by phi n if m is equal to n. Okay? And this is the property of the orthogonal function. So here, look here, what happens? It happens that this quantity, phi2 common phi fx common t bar is equal to, when you multiply phi2 by phi1, you have 0. When you multiply phi2 by phi2, you have this. You have phi2 common phi2 multiplied capital F to a function of time. This is x, 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 x. Okay, so this is F2. So F2, F sub 2 is a time function defined like the projection of f, x, and t by phi2. And after this integral, you have only a time bar function divided by the module of this base function phi2, comma phi2. And so, at the end of the story, if you have as an equation f equal to 0, this equation is identical to a set of equations f. If you have, let me write here, if you have to impose f xt equal to 0, and you have a set of orthogonal functions, this is equivalent to write f n of time equal to 0 for n equal to 1, 2, 3. As a mathematician, I have finished my job because I have transformed this initial partial differential equation to this set. I have one partial differential equation which is transformed to a set of infinite ordinary differential equation like this. And I think that this lesson is one of the most important lessons for mechanical engineering, for narrow space engineering. Note that at the basis of this, you need to have a set of orthogonal functions. And you have to introduce the orthogonal function. And this is the point. Now there is an important, and now I can pass to the part 2 of this discussion. In this part 1, we have essentially introduced a set of orthogonal functions, generic set of orthogonal functions, and we have demonstrated that if we have a set of infinite orthogonal functions, orthogonal is better than independent, is orthogonal. If I have a set of orthogonal functions, instead of solve this equality here for finding a solution, the original problem is this. Excuse me. This original problem can be transformed identically, not approximately, identically to this set of final equations. And I can guarantee that what I obtain, putting this infinite equation to 0 is identical to put my original differential equation to 0. Okay? First part. Now, second part. How can I get orthogonal function? How can I find orthogonal function to be used for solving my problem? And then I can also give you some result for this. These results are very important. I cannot develop this statement in details. People who is interested can ask me, I can give the material, but I'm giving you now some essential and important results by structural dynamics of continuous structures. Okay, so the answer of this question is the following. A set of orthogonal function can be generated by any structural operator of a continuous structure. Examples, some continuous structure, our beam undergone to a flow. We have the equation of our beam is the following. I could copy this, but it's this equation here. And if you consider the equation, the first part of the equation, AI W4 plus N bar W second plus KW plus the other part. This part here can be symbolically described like L structure operator as applied to W. And so the structure operator is the following, is a differential operator composed by a first part with this fourth derivative in space by IE, this n multiplied by the second derivative, and then by k multiplied by W. So the structure operator is essentially the operator giving to you the conservative portion of the elastic force imbalance. You have here all elastic force involved to your problem. You have the first term, which is the term of the elastic beam restoring its initial position. The second term is another elastic term related to the buckling membrane force, which are conservative force, but please before the buckling event, before the buckling. But this force is conservative because it's quite conservative. Because a force generated by an external field of conservative force, buckling is a constant force in space. Last, we have our stiffness band, K, which is another kind of conservative force. So, this is our operator. And what about the eigenfunction? What about the orthogonal functions? we can generate always orthogonal function by solving this space problem. Problem is ls phi n equal to lambda n phi n. Okay, plus the boundary condition. So in our case, we can consider our system, but just avoiding the aerodynamic force, this term, the damping, and this term, the aerodynamic damping. So leaving only this part, the elastic part, the conservative part, apart the initial force. Okay? So you will always generate orthogonal function if you take this operator and solve the following problem. When the operator applied to the function is able to give you the same function multiplied by a constant, is this problem similar to other problems you encountered in your life? Yes, probably you encountered this problem. Matrix x vector is equal to lambda vector. Okay? What about the difference between this problem and this other problem? This problem here is algebraic and currently is an eigenvalues problem. And at the end of this problem, you are able to evaluate the constant lambda and the vector x. This here is not an algebraic problem, but is PDE problem, only space problem. Only space now, please, only space. And this kind of problem is also known as eigenproblem. Eigenproblem for determining an eigenfunction phi and an eigenvalue lambda. So we don't have eigenvector here, but we have eigenfunction. So psi are eigenfunction. Excuse me, psi, phi. Phi are eigenfunction of the structural operator ls. So by solving this partial differential problem, we obtain the eigenfunction phi and the eigenvector lambda. This is a strange problem. It's not an algebraic eigenproblem, but is a functional eigenproblem. Ladies and gentlemen, we are studying currently space at infinite dimension, not space at finite dimension. But the parallelism is quite absolute. You have an infinite dimension instead of to have a finite dimension. So you have an infinite number of eigenvalues and eigenvector, not a finite number. Because the solution of this problem here is not for 3 eigenvalues, but for infinite eigenvalues, consistently, okay? Eigenvalue, excuse me. Okay. Eigenvector. Okay. The important result for us is the following, and then I stop for a pause. the eigenfunction obtained by any structural operator are always orthogonal. Another theorem, the eigenvalues obtained by any structural operator are always real and positive. Always, please, always. And therefore, we are authorized to call lambda n as the square of a quantity, or the word used as quantity squared omega. Probably you know very well this. Okay, I stop here. I want just to stop giving you an information. The information is the following. For any homogeneous body, elastic body, this eigenfunction and these eigenvalues correspond for continuous elastic body to the concept of mode of vibration. These quantities are, for an homogeneous, mass homogeneous, mean, these quantities are exactly the physical concept of mode of vibration, and the corresponding lambda are the square of the so-called frequency or radiant frequency of vibration. Okay? I take a pause of a few minutes for you. Of course, if you want, I can continue, but I have to stop. Okay?